In the cold, clear skies over Chile, the giant eyes of the Paranal Observatory turn towards the heavens. The domes of the European Southern Observatory's very large telescope rotate, aligning to track a visitor from beyond our cosmic neighborhood. Interstellar object 3IATLAS 2 has crossed into our solar system, carrying with it the chemical fingerprints from a planetary system not our own. Using the incredible power of the very large telescope, astronomers observed its coma, its atmosphere, from a state of deep quiescence all the way to a measurable glow. This is the story of how dust, a simple molecule called the CN radical, and even atoms of neutral nickel revealed the secrets of a changing, distant visitor. No spacecraft has ever reached an interstellar comet. The distances are simply too vast, and the warning we get is too short. But even from Earth, we have a powerful tool: high-resolution spectroscopy. This technique allows us to break down the faint light from distant objects into a rainbow of colors, revealing what the object is made of and how it behaves as it warms up on its journey toward our sun. 3IATLAS 2 is only the third known interstellar object to visit us, following the enigmatic ʻOumuamua and the active comet 2I Borisov. We believe it's a fragment, a piece of a small planet-like body called a planetesimal, that was violently ejected from its home star system long ago. For astronomers, this is a golden opportunity. It's a chance to study the chemistry of volatiles, the ices that make comets active, and the physics of dust from a place that is unt our solar system. It's a direct sample from another world, delivered right to our cosmic doorstep. With the 3IATLAS 2 being incredibly faint and far away, only a telescope, with the immense light-gathering power and spectroscopic sensitivity of the Very Large Telescope, or VLT, could track its evolving activity. The VLT is actually a group of 4 telescopes, each with a mirror 8.2 meters across. Combined, they create a virtual mirror of immense size. Instruments like X-Shooter and 4S2 are designed to capture the full spectrum of light, from the ultraviolet all the way to the near-infrared. This broad wavelength coverage is absolutely essential for detecting the weak emission lines from gases in a comet's coma, especially when it's at a great distance from the Sun. At first, 3IATLAS 2 looked dormant. When astronomers first pointed the VLT at it, the initial observations showed a very weak, continuous spectrum of light, dominated mostly by reflected sunlight. It was behaving like an inactive interstellar rock. Its dusty coma, the cloud of material surrounding the nucleus, was barely detectable. There was no measurable outgassing of the typical cometary volatiles we expect to see, like water, carbon monoxide, or carbon dioxide. At this great distance from the Sun, the object appeared to be in a deep, frozen slumber. But as the object continued its journey, drawing ever closer to the Sun, that began to change. VLT photometry, which measures the brightness of the object, revealed that a faint coma was beginning to emerge. Its brightness was increasing, driven mostly by sunlight, scattering off tiny dust grains. This was a crucial clue. There were still only very weak signs of gas, which suggested that the activity was being led by the lifting of solid grains from the surface, rather than the sublimation of ices into gas. The dust-to-gas ratio appeared to be high, a behavior remarkably similar to what was seen in the early, distant observations of our previous interstellar visitor, 2I Borisov. Even before any major release of gas, the physics of the dust told astronomers that something profound was changing deep beneath the object's surface. But how can dust become active when the object is still so far from the Sun? In these distant reaches of the solar system, sunlight is weak, but it is not powerless. Over long timescales, it can trigger deep-seated processes within the cometary nucleus. One such process is the transition of water ice from an amorphous, disorganized state to a more stable crystalline form. This change releases a burst of energy, which can vaporize other, more volatile ices trapped within the water ice matrix. This sudden release of gas can fracture the surface and launch dust grains into space. Even the gentle sublimation of super-volatile ices, like carbon monoxide, which can happen at very low temperatures, can disrupt the dusty mantle on the surface. These thermal gradients create stress, causing the surface to crack and shed its dusty outer layer. So, well before the classic cometary activity of water sublimation begins, these subtle processes can liberate dust, giving us our first hint of an awakening giant. Then, the first definitive chemical signal appeared. The VLT detected the faint glow of the CN radical, also known as cyanogen. CN is a trace species in comets, meaning it's not very abundant, but it's highly diagnostic of early-stage activity. It often results from the breakdown of more complex, nitrogen-bearing molecules, like hydrogen cyanide, when they are exposed to solar radiation. Astronomers watched as the strength of the CN signal slowly began to rise as 3I-ATLAS 2 decreased its distance from the Sun. When CN appeared, astronomers saw the first clear chemical signal from an interstellar nucleus. Its gradual brightening marked the transition from activity dominated purely by dust to genuine, volatile release. In the field of cosmic forensics, CN is a fingerprint. Because it traces the chemistry of nitrogen-bearing molecules, it can tell us a lot about the object's origins. In our previous interstellar visitor, 2I Borisov, the amount of CN was unusually strong compared to other gases, suggesting its home system was rich in certain types of nitriles. By carefully comparing the CN strength in 3I-ATLAS 2 to that of Borisov, and our own solar system's comets, astronomers can begin to piece together whether its natal environment had similar or distinctly different chemistry. Even these faint lines of light, traveling across trillions of miles, can reveal the chemical ancestry of a world that formed around a distant, unknown star. And just when the story was becoming clear, the VLT revealed a surprise. The data showed a distinct emission line from neutral nickel atoms. This was remarkable. Nickel is a refractory element, meaning it's a metal that typically stays locked inside solid grains and requires very high temperatures or violent fragmentation to be released as a gas. Yet here it was, drifting freely in the cold environment of a distant comet's coma. This same strange phenomenon had been detected in solar system comets by the VLT in just the past few years, and finding it in an interstellar object was a major breakthrough. It demonstrates that the physical mechanisms responsible for releasing metals from cometary dust are not unique to our solar system. They are universal, happening in comets across the galaxy. This subtle emission line of neutral nickel, an element forged in the heart of ancient supernovae, was now tying 3I-ATLAS 2 to both our local and its extrasolar comet families, connecting our own cosmic backyard to the vast galactic neighborhood beyond. So, what does this mysterious nickel vapor tell us about the comet itself? The answer lies in the dust. The nickel seems to be coming from extremely tiny grains, particles less than 100 nanometers across. When sunlight hits these microscopic dust grains, they heat up rapidly. Even though the comet is far from the sun and the ambient temperature is incredibly low, this solar heating is enough to cause the minerals within the grains to sublimate, turning directly from a solid into a gas. This means the nickel isn't just floating around freely. It's a direct tracer, a fingerprint of the mineral makeup and the thermal history of the comet's dust. The presence of gas-phase nickel strongly suggests that these microscopic grains are being heated and cracked apart, exposing the mineral cores of the comet's dust population for us to see. To truly understand a dynamic object like a comet, a single snapshot is never enough. That's why the team used the Very Large Telescope to watch 3I-ATLAS 2 over an extended period. This time series spectroscopy was crucial. As they watched, they saw the emission lines from both cyanogen and nickel steadily increase in intensity. At the same time, the dusty coma surrounding the nucleus grew in size and brightness. But this evolution wasn't smooth or predictable. The changes came in fits and starts, with sudden boosts in activity. This tells us the comet's nucleus isn't a uniform ball of ice and rock. Instead, these episodic bursts hint at a complex, rotating body with distinct patches on its surface, or perhaps diverse reservoirs of material hidden just beneath the crust. By observing the object repeatedly, the VLT team mapped how its activity fluctuated. The pattern was neither uniform nor predictable, clear signs of a complex rotating nucleus with diverse material reservoirs. One of the most fascinating things about 3I-ATLAS 2 is just how far from the sun it started to wake up. We could measure cyanogen gas while it was still deep in the outer solar system, a region where water ice remains frozen solid. For typical comets from our own solar system, activity at this distance is rare because they are mostly driven by the sublimation of water. So, what's powering this interstellar visitor? The prime suspects are what we call hypervolatiles, like carbon monoxide or carbon dioxide. These substances turn to gas at much colder temperatures than water. The thinking is that the gentle warming from the distant sun is enough to sublimate CO or CO2, which then drags deeper, more complex materials up to the surface and out into the coma. This might be a common trait for interstellar comets. They likely formed in the frigid outer regions of their home star systems, colder than where our own comets formed. As a result, 3I/ATLAS 2's distant glow shows that interstellar objects can activate long before crossing the water ice line. These objects may preserve volatile inventories, unlike those of typical solar system comets. 3I/ATLAS 2 is now the third interstellar object we've seen up close, and it's teaching us that there's no single type of interstellar visitor. Each one has been a unique character. First, there was 1I/ʻOumuamua. It was completely enigmatic. We saw no detectable coma of gas or dust, yet it was accelerating away from the sun faster than gravity alone could explain. Something was pushing it, but we don't know what. Then came 2I Borisov, which was much more familiar. It looked and acted like a classic comet from our own Oort cloud, showing strong signs of carbon monoxide, cyanogen, and other gases. It was a hypervolatile rich comet, just as we might expect. And now we have 3I/ATLAS 2, which seems to be an intermediate case. It started with weak but steady activity, dominated by dust. Over time, its gas production slowly ramped up. 3 interstellar visitors, 3 different personalities. Together, they show that planetary systems across the galaxy produce a wide range of icy bodies. So, the big question remains, what is the engine driving this comet's activity? The data gives us several tantalizing possibilities, and the reality is likely a combination of them. The first and most obvious driver is the sublimation of hypervolatiles like carbon monoxide and carbon dioxide, turning to gas at cold temperatures. Another idea involves amorphous ice. This is a special, disorganized form of water ice that can trap other gases within its structure. As it's gently heated, it can release these trapped gases, triggering activity. A third mechanism could be the fracturing of dust grains we talked about earlier, where solar heating causes thermal stress that cracks the particles and releases volatiles. Finally, all of this could be happening in localized jets on the comet's rotating nucleus, creating those unpredictable bursts of activity. The exact balance remains uncertain, but the VLT data point toward a nucleus that becomes increasingly active as sunlight penetrates deeper layers. This brings us to why long-term monitoring is so absolutely essential. If we had only taken a single picture of 3I/ATLAS 2, we would have missed the entire story. By watching it over time, we can start to reconstruct the different layers of volatile materials within its nucleus, almost like peeling an onion. We can track outbursts, asymmetries in the coma, and how its activity changes as it rotates. This continuous stream of data allows us to directly compare the evolution of an interstellar comet with that of comets from our own solar system, highlighting key differences in their composition and history. Most importantly, it reveals the physical processes unfolding on a world from another star system in real time. Looking at a single snapshot cannot reveal a comet's internal story. Only time series monitoring shows how an alien world breathes out its chemistry. With each faint emission line, 3I/ATLAS 2 whispered clues about its birthplace, its evolution, and the universal physics of icy bodies. The Very Large Telescope captured those whispers, turning a dim comet into a rich scientific archive. Our solar system may only borrow these interstellar visitors briefly, but the knowledge they bring is permanent. They expand our understanding of how planetary systems form and the incredible diversity of worlds that exist beyond our own. Thanks for watching. If you enjoyed this journey to the outer reaches of our solar system, don't forget to like and subscribe for more deep dives into the cosmos.